Imagine looking up at the night sky and knowing that right now, just beyond the edge of our atmosphere, something extraordinary is happening. A factory is orbiting our planet, not assembling spacecraft, but creating things we once believed could only be made on Earth. Perfect crystals for lightning-fast computers, human tissue for medical miracles, alloys stronger and lighter than anything ever forged in gravity. This is not a scene from a distant future. This is today. This is the story of how we got here, a journey as daring as it is real, born from a simple but profound question. What if the best place to build the future isn't on the ground, but above it? This is the story of Earth's first orbital factory, a triumph of vision, courage, and collaboration that marks nothing less than the beginning of a new industrial age. For centuries, manufacturing has been bound by the limits of our planet's gravity, atmosphere, and environmental constraints. But up there, in the silent, weightless expanse of space, those rules simply don't apply. We're talking about a facility that operates in a near-perfect vacuum, where materials can be formed without impurities, where biology behaves differently, and where innovation isn't just encouraged, it's necessary. This isn't just about making things in space, it's about making things possible for the first time. Over the course of this video, we'll walk step by step through the entire timeline of this breathtaking achievement. We'll meet the dreamers who first imagined it, the engineers who designed it, and the global teams who built it under conditions more challenging than most of us can fathom. We'll explore the setbacks that nearly ended the project, the breakthroughs that saved it, and the moments of pure wonder that reminded everyone why it mattered. This is a story about us, about human curiosity, stubbornness, and our incredible ability to reach beyond what seems possible. So settle in. You're about to witness one of the most ambitious projects humanity has ever undertaken, and understand how it's already changing life down here on Earth. Long before the first metal beam was forged for this endeavor, the entire project existed solely as a spark of imagination in the minds of a few extraordinary individuals. These were not just scientists or engineers, they were true visionaries who could look at the empty vastness of space and see a bustling hub of industry, a place where the very laws of physics could be harnessed for creation. One of the earliest and most influential of these thinkers was a physicist named Gerard K. O'Neill. Back in the 1970s, while many were focused solely on planting flags on moons, O'Neill was designing entire cylindrical space colonies in meticulous detail. He asked a revolutionary question: is the surface of a planet really the right place for an expanding technological civilization? His answer was a resounding no. He envisioned massive, self-sustaining habitats built from materials extracted from the moon and asteroids, complete with farms, factories, and towns. His book, The High Frontier, became a Bible for a generation of space enthusiasts, providing a serious, physics-based argument for living and working in space. It was O'Neill who first rigorously proposed that the microgravity and vacuum of space could be used not just for exploration, but for manufacturing things we could scarcely dream of on Earth. This philosophical groundwork laid by pioneers like O'Neill was essential, but it needed modern champions with the resources and audacity to make it seem plausible to the wider world. Enter the era of the billionaire space entrepreneurs. Figures like Jeff Bezos, the founder of Blue Origin, frequently cite Gerard O'Neill as a direct inspiration for their entire corporate mission. Bezos doesn't just talk about rockets, he talks about a future where millions of people live and work in space, and he argues that moving heavy industry off Earth is the only way to preserve our planet. It's a compelling environmental argument to protect the Earth, we must leave it for our most demanding industrial processes. Similarly, Elon Musk's drive with SpaceX, while initially focused on transportation and Mars colonization, fundamentally changed the economic calculus. By relentlessly pushing the cost of launch down through reusable rocket technology, Musk made the entire concept of regularly supplying an orbital factory financially conceivable for the first time. These modern innovators provided the crucial bridge between 20th century theory and 21st century practicality, combining a grand vision with the engineering grit and business acumen to attract serious investment. Their advocacy moved the idea from the fringes of academic conferences into the boardrooms of Fortune 500 companies. They emphasized tangible, market-ready products that could only be made in the unique environment of space. Imagine growing perfect, flawless crystals for semiconductors without the distorting effects of gravity, leading to computers that are orders of magnitude faster and more efficient. Or picture bioprinting complex human organs with delicate vascular structures that would simply collapse under their own weight on Earth, potentially ending transplant waiting lists forever. Envision blending metals that simply don't mix well down here, creating entirely new superalloys that are lighter than aluminum but stronger than titanium, revolutionizing everything from air travel to medical implants. These weren't just pipe dreams, they were demonstrable facts from early experiments on the International Space Station. The visionaries took these scientific curiosities and wove them into a powerful narrative of economic and humanitarian benefit, a story compelling enough to inspire a new generation of engineers, scientists, and investors to dedicate their careers to this audacious goal. This collective leap of faith, from abstract dream to a shared mission, set the entire stage for humanity's first off-world industrial endeavor. Translating that grand vision into a physical reality began not with metal and wire, but with lines of code and digital models. The first monumental task was to create conceptual designs that could withstand the brutal honesty of space. This was the phase where poetry met physics, where the dream of a zero-gravity factory had to be hammered into a set of unforgiving, practical blueprints. Teams of aerospace engineers, material scientists, and even architects who were more accustomed to designing skyscrapers found themselves collaborating on the most unusual structure of their careers, one that would never feel the pull of gravity or the pressure of wind. Their primary goal was adaptability. They weren't designing a single-purpose machine, but a versatile industrial park that could one day host a semiconductor cleanroom and, in another module, a delicate bioprinting lab for human tissues. This need for flexibility led to a modular approach, envisioning a central spine or truss to which various specialized units or pods could be attached, replaced, or upgraded as needed, much like adding new rooms to a house or new apps to a smartphone. Every single design decision was a battle against the extreme environment of low Earth orbit. How do you shield sensitive electronics and any future human crew from the constant, DNA-damaging barrage of cosmic radiation? The answer wasn't just thick walls of aluminum, which would be prohibitively heavy to launch. Engineers explored innovative materials like polyethylene infused with hydrogen, a surprisingly effective radiation barrier, and even considered using tanks of water or waste as part of the shielding, a regenerative and multi-functional solution. The threat of orbital debris traveling faster than a bullet demanded a dual approach: Whipple shields, which are layered outer walls designed to vaporize an incoming particle upon impact, and advanced detection systems that could alert the factory's navigation thrusters to perform avoidance maneuvers. Power autonomy was another colossal challenge. While vast solar arrays were the obvious answer, their design was anything but simple. They had to be compactly stowed for launch, then unfurled or assembled robotically in space, all while being engineered to withstand wild temperature swings from blazing sunlight to deep shadow every 90 minutes. To solve these puzzles long before any hardware was built, teams relied on incredibly sophisticated computational models. They created high-fidelity digital twins of the entire facility, simulating the stresses of launch vibrations, the subtle forces of solar pressure on large surfaces, and the precise choreography of robotic assembly in a weightless environment. These simulations were crucial for testing assembly techniques, allowing engineers to practice how a robotic arm would maneuver a multi-ton module into its docking port with millimeter precision, all with the time delay of a signal traveling from Earth. They modeled fluid dynamics to understand how liquids would behave in manufacturing processes without gravity to settle them, and thermal dynamics to prevent equipment from freezing or overheating. These conceptual blueprints, therefore, became far more than just technical drawings. They were dynamic, living documents and virtual proving grounds. They told a story of human ambition, mapping every bolt, every wire, and every contingency plan, building an unprecedented future one digital component at a time. This exhaustive design phase provided the essential roadmap and the crucial confidence that such a feat was indeed achievable, setting the stage for the next enormous challenge, convincing the world to pay for it. But a vision, no matter how brilliantly designed, remains a fantasy without the fuel to make it real, and the fuel for a project of this magnitude was capital, an almost unimaginable amount of it. Transforming those exquisite digital blueprints into hardware hurtling through space required building one of the most unusual and robust financial ecosystems ever conceived. This wasn't just about finding a single deep-pocketed investor. It was about weaving together a tapestry of funding from vastly different worlds, from the cautious halls of government agencies to the high-risk, high-reward arenas of Silicon Valley. The strategy was multi-pronged, recognizing that the risk was too great and the payoff too far in the future for any single entity to shoulder alone. The first crucial layer of support came from the established giants of space exploration, NASA, the European Space Agency, and their international counterparts. These agencies didn't write blank checks for construction. Instead, they funded the essential yet less glamorous foundational research. They issued grants for advanced studies on material behavior in microgravity, sponsored university competitions to solve specific technical hurdles like debris shielding, and awarded contracts to develop and test prototype manufacturing systems on the International Space Station. This government backing was vital. It de-risked the core technologies, providing the public validation and scientific credibility that private investors needed to see before they would even consider opening their wallets. It sent a powerful signal that this was a serious national and indeed global priority. Simultaneously, a parallel financial engine was roaring to life in the private sector. The billionaires who had championed the vision, like Bezos and Musk, weren't just cheerleaders, they were the first major financiers. Through their companies, Blue Origin and SpaceX, they invested heavily not only in their own launch capabilities, but also in the nascent startups that were springing up to focus exclusively on space manufacturing. This created a powerful synergy. The same companies that would provide the transportation were also funding the customers who would need rides. Alongside them came venture capital firms, traditionally focused on software and biotech, who began to see orbital manufacturing as the ultimate moonshot, a sector with the potential for astronomical returns. They injected billions into startups promising to build everything from space, made fiber optics to pharmaceuticals, betting on the future market value of products that were impossible to create on Earth. This venture capital wasn't patient money. It came with expectations of rapid growth and a clear path to profitability, which in turn forced these young companies to move quickly and focus on demonstrable, near-term milestones. Perhaps the most surprising and democratizing element of the funding model was the use of crowdfunding campaigns and strategic corporate partnerships. While the sums raised from the public were a tiny fraction of the overall budget, they served a purpose far greater than their dollar value. They were a marketing tool and a legitimacy machine. When tens of thousands of ordinary people contributed, it proved there was widespread public enthusiasm and buy-in for the project, making it easier for politicians and corporate boards to justify their own, much larger investments. More importantly, it began to forge a sense of collective ownership. This wasn't just a factory for governments and billionaires, it was humanity's factory. The corporate partnerships were equally strategic. Instead of just asking for donations, the project's leaders offered something of immense value: future manufacturing capacity. They went to major tech and pharmaceutical companies and presented a compelling business case. Become an anchor tenant, they proposed. Secure a dedicated slot in our orbital facility now at a pre-construction price, and you will have exclusive first access to materials that will give you an insurmountable competitive advantage. For these companies, it was a calculated gamble on R&D, a way to ensure they wouldn't be left behind in the next industrial revolution. Their buy-in provided a crucial stream of upfront capital, and more importantly, a list of real-world customers waiting for the factory to come online. Key financial milestones marked the project's journey from idea to inevitability. The first was securing those initial multi-million-dollar grants for detailed feasibility studies, which moved the conversation from if to how. The next was the closure of the Series B funding round for the lead startup, bringing in over $1 billion from a consortium of venture firms and strategic partners. But perhaps the most significant moment was the signing of the first anchor tenant, a major semiconductor manufacturer, to a long-term contract. This wasn't just funding, it was market validation. It proved there was a commercial demand for the products, which in turn attracted even more investment. This continuous flow of capital did more than just pay the bills, it accelerated the entire timeline. It allowed for the parallel development of multiple prototype systems instead of a cautious, sequential approach. It funded not just one, but several testing cycles, enabling rapid iteration and learning from failures without jeopardizing the entire mission. The financial backing demonstrated a powerful and growing consensus across society that orbital factories were not merely a fascinating science experiment, but a viable, profitable, and necessary step forward for human civilization. With a monetary foundation firmly in place, the next critical task began: scouring the globe to find the brilliant, relentless, and unconventional minds who could turn this well-funded dream into a tangible reality. With the financial runway secured, the mission's success now hinged on a factor far more complex than capital: people. Assembling the right team was not a matter of simply posting job listings. It was a global talent hunt for a new breed of pioneer. This wasn't about finding individuals who could just do a job, but visionaries who could invent their roles from scratch, solving problems that had never been encountered before. The recruitment net was cast wide, targeting a wildly diverse set of disciplines. Headhunters sought out the world's leading experts in robotics, not for factory floors on Earth, but for machines that would need to operate with delicate precision in the unforgiving void of space. They needed aerospace engineers who understood orbital mechanics and the subtle, constant threats of the space environment. Materials scientists were essential to select and test components that could withstand radical temperature swings and radiation without failing. Specialists in sustainable design were brought on to create the closed-loop life support systems that would make the factory not just functional, but self-sufficient. The backgrounds of these recruits read like a map of modern innovation. Many came directly from legacy space programs like NASA or the European Space Agency, bringing with them hard-won experience from missions to the International Space Station or the development of deep space probes. Others were poached from the cutting edge of terrestrial industry, from semiconductor clean rooms, from automotive assembly lines pushing the boundaries of automation, and from advanced pharmaceutical labs. Perhaps most surprisingly, the team also included veterans from the video game industry. Their expertise in creating incredibly detailed, physics-based virtual environments was invaluable for building the simulators that would train both the AI and the human operators. They knew how to model complex, multi-step assembly sequences in a digital space, allowing the team to practice and perfect every bolt and wire connection long before any physical hardware was at risk. This fusion of traditional space-hardened experience with fresh, disruptive thinking from other sectors created a culture that was both rigorously practical and wildly inventive. Managing such a geographically and culturally dispersed team required a radical approach to collaboration. This was long before the world embraced remote work. This project helped pioneer it. They utilized advanced digital collaboration platforms that were a step beyond video conferencing. These were immersive virtual workspaces where an engineer in Tokyo could manipulate a 3D model of a docking mechanism in real time alongside a colleague in Munich, while a programmer in California annotated the design with notes. They worked across every time zone, creating a truly 24/7 development cycle where the project literally never slept, seamlessly handed off from one regional hub to the next. To forge this group of brilliant individuals into a cohesive, resilient unit, they didn't rely on standard corporate retreats. Instead, they embarked on intense team-building exercises designed to simulate the pressures they would face. Teams were sent to remote analog habitats like those in the Utah desert or on the slopes of Hawaiian volcanoes to live and work together in isolation, solving engineering problems with limited resources, a direct parallel to future operations in space. They spent countless hours in VR rigs, not playing games, but physically practicing the intricate ballet of orbital assembly with virtual reality tools, building muscle memory for tasks they would one day perform remotely from a control room on Earth. This carefully curated, intensely bonded cohort became more than just a workforce. They became the living, breathing backbone of the entire endeavor. They were united by a shared sense of purpose that transcended individual ambition, driven by the knowledge that they were building something that would change history. Their culture was one of radical transparency and fearless iteration, where any idea could be challenged and any failure was treated as a learning opportunity, not a mark of shame. This blend of cutting-edge expertise across dozens of fields, combined with an almost unwavering passion and a proven ability to work as a single, global unit, created an intellectual engine of unprecedented power. This collective genius, however, was about to be put to the ultimate test. The theoretical models and optimistic blueprints were set aside. It was time to confront the cold, hard, physical laws of the universe and tackle the immense technical hurdles that stood between a dream on a screen and a factory in the sky. The sheer scale of the engineering obstacles facing the team was almost beyond comprehension. They weren't just building a structure, they were inventing an entirely new discipline of construction, one where every single rule from terrestrial engineering had to be questioned, tested, and often completely rewritten. The first and most fundamental challenge was the paradoxical nature of microgravity itself. On Earth, Gravity provides a constant, predictable downward force that gives structures stability and allows builders to easily anchor themselves and their tools. In orbit, that foundational force vanishes. A simple turn of a wrench could send an astronaut or a robot spinning uncontrollably, and without careful counterbalancing, the reaction forces from any activity could send the entire factory into an unwanted tumble. To solve this, engineers devised incredibly sophisticated magnetic anchoring systems. These weren't just simple magnets. They were precisely controlled electromagnetic soles for robotic feet and grippers that could instantly lock onto ferrous surfaces on the factory's frame, providing a stable platform for work, then release without a push-off, allowing for smooth, controlled movement. This system gave the assembly robots the stability of a mountain climber clipped into a sheer rock face, but in 3 dimensions. Beyond the simple act of moving around, the environment itself was a relentless adversary. The factory would be bombarded by cosmic radiation, a constant sleet of high-energy particles that could fry sensitive electronics, degrade materials, and pose a serious health risk to any future crew. Shielding couldn't rely on simply piling on heavy metals, as every extra kilogram launched from Earth cost a fortune. The solution was a brilliant piece of multi-functional design. Engineers planned to use the factory's own water and waste storage tanks as a radiation barrier, strategically placing them around the habitat modules to protect the occupants. For the electronics, they selected radiation-hardened components and designed redundant systems that could be powered down or isolated during periods of intense solar activity. Then there was the threat of the microscopic micrometeorites and tiny pieces of orbital debris traveling at over 17,000 miles per hour. A collision with even a fleck of paint could be catastrophic. The answer came from the lab: self-healing polymers. These remarkable materials, when punctured, would undergo a chemical reaction to seal the breach, much like human skin clotting a wound. Layered with advanced Whipple shields, thin, sacrificial outer walls designed to vaporize an incoming particle, the factory's hull could protect itself from all but the largest impacts. Powering this industrial outpost was a puzzle of immense proportions. The energy demands for manufacturing processes like melting metal alloys or running banks of computers were enormous. While vast, delicate solar arrays were the primary solution, their design was a nightmare of conflicting requirements. They had to be compactly stowed for launch, then unfurled or assembled by robots into structures the size of football fields, all while being strong enough to withstand the constant thermal cycling from searing sunlight to deep freezing shadow every 45 minutes. To ensure uninterrupted power during the orbital night, engineers integrated massive lithium-ion battery arrays, but also explored a far more futuristic concept: wireless energy transmission. Experiments were conducted to beam power via microwaves or lasers from dedicated solar satellite stations in higher, sunnier orbits, creating a resilient, multi-source energy grid that wouldn't be wholly dependent on the factory's own panels. Perhaps the most critical system of all was the one designed to keep itself alive. The life support system had to be a masterpiece of closed-loop efficiency, recycling 98% of water and air because a resupply mission from Earth could not be guaranteed on a weekly basis. This went far beyond the systems on the International Space Station. Engineers designed advanced bioreactors that used specially selected strains of algae and bacteria, not just to scrub carbon dioxide from the air, but to convert human waste into clean water and even nutrient-rich biomass that could, in theory, be used to support plant growth for future food production. Every exhaled breath, every drop of sweat, every bit of wastewater was seen not as refuse, but as a valuable resource to be captured and purified back into the system. To battle-test every one of these solutions against the infinite unknowns of space, the team relied on a digital doppelganger, a supremely detailed computational model of the entire factory. This virtual twin lived in a server farm on Earth, but it experienced a simulated version of every trauma the real factory might face. Engineers would run endless stress test scenarios, unleashing virtual solar flares of unprecedented strength, directing waves of simulated debris at the hull, and triggering multiple cascading system failures to see how the design would hold up. They modeled the fluid dynamics of molten metals in zero gravity to predict how they would behave in the manufacturing furnaces, and they simulated the subtle, cumulative effects of solar radiation pressure on the massive solar arrays to ensure the factory's orientation thrusters could compensate. Each solved problem, each simulation that ended in success, added another layer of confidence and robustness to the blueprint. What began as a collection of brilliant but untested ideas was slowly, painstakingly forged into a viable engineering plan, a set of solutions that could survive the brutal honesty of space. With these formidable technical hurdles now mapped and overcome in theory, the next logical step was to move out of the digital world and into the physical, to see if these ambitious designs could actually hold up in the real world. The leap from flawless computer models to physical hardware is where theory meets its most unforgiving critic, reality. This critical phase demanded building not the entire factory, but its essential components in miniature, subjecting them to a battery of torturous tests designed to be even harsher than the actual conditions of space. The goal was simple: find the failures on Earth where they could be fixed with a wrench and a whiteboard, not in orbit where a single flaw could doom a billion-dollar mission. The primary arena for this trial by fire was a network of massive vacuum chambers, stainless steel cylinders large enough to hold entire prototype modules. Inside, engineers could pump out all the air, creating a near-perfect void that mirrored the emptiness of space. Here, they observed how materials behaved when stripped of an atmosphere. Would seals hold without air pressure to keep them tight? Would lubricants evaporate or turn gummy? The chambers answered these questions, revealing which materials were truly space-worthy and which were not. But replicating the vacuum was one thing. Simulating the weightlessness of orbit was an entirely different challenge. For that, the team turned to a famously stomach-churning tool, the parabolic flight. They outfitted a specially modified aircraft, often nicknamed the Vomit Comet, with a test rig holding a prototype robotic arm or a docking mechanism. The pilot would then fly a series of steep climbs and sharp dives, creating 20 to 30 seconds of precious microgravity at the apex of each arc. Inside, engineers and scientists, often strapped down themselves, would watch with rapt attention as their creations floated and operated in this brief window of zero-G. These flights were chaotic, expensive, and physically demanding, but they provided invaluable live action data on how mechanisms would perform without gravity to guide them. Could a robotic hand successfully grasp a floating component? Would a hinge deploy as expected? The parabolic flights caught 100 tiny flaws that static testing would have missed, from fasteners that worked loose to wiring that floated into dangerous positions. Back in the lab, another revolution was underway: additive manufacturing. High-precision 3D printers were used to create detailed scale models of the factory's most complex modular components, from custom tool interfaces to the intricate lattice structures of the central truss. These models weren't just for show, they were subjected to brutal stress tests. They were placed in thermal cycling chambers that swung from -250 degrees Fahrenheit to over 250 degrees in minutes, simulating the extreme temperature shifts of each 90-minute orbit. They were vibrated on massive shaker tables that replicated the violent, bone-jarring forces of a rocket launch, ensuring nothing would crack or resonate at a fatal frequency. This iterative process of print, test, break, and redesign allowed for rapid evolution of parts, optimizing them for strength and weight savings long before the final versions were machined from expensive aerospace-grade alloys. Perhaps the most surreal and crucial testing environment was not in the sky but under the sea. The team partnered with NASA's Extreme Environment Mission Operations Program, utilizing giant underwater training facilities like the Neutral Buoyancy Lab. This massive pool, containing enough water to fill several Olympic swimming pools, is a stand-in for space. Here, weighted and balanced in their bulky suits, teams of divers standing in for both astronauts and robots could practice the intricate, slow-motion ballet of assembly. They would spend hours underwater, rehearsing how to maneuver a multi-ton solar array into its mounting bracket or how to replace a faulty pump module, all while managing tethers and tools that wanted to float away. These underwater sessions were less about testing the hardware itself and more about testing the procedures, revealing the countless hidden complications in what seemed like a simple task on paper. They highlighted communication delays, tool accessibility issues, and the sheer physical and mental fatigue of complex work in a weightless environment. This relentless campaign of prototyping and testing was not just about confirming what worked, it was about actively hunting for what would fail, and it found problems no simulation had predicted. One of the most persistent and surprising issues was electrostatic discharge. In the dry vacuum of space, the factory's components, especially non-metallic composites, were prone to building up significant static electricity from the constant flow of solar wind and the movement of internal machinery. This invisible threat could arc between components, silently frying delicate circuit boards and sensors. The solution was an elegant one, embedding a fine, almost microscopic grid of conductive material into composite surfaces, creating a safe path for static charges to dissipate without causing damage. Another unforeseen challenge was outgassing the tendency for certain plastics and adhesives to slowly release trapped gases in a vacuum. These gases could then condense on critical surfaces like camera lenses or solar panel glass, clouding them and degrading performance. This led to a painstaking review of every single material used, switching to low outgassing alternatives for even the most mundane components. Each solved problem, each design iteration prompted by a test failure, was not a setback but a step forward. Every crack identified in a vibration test, every electrostatic zap in the vacuum chamber, every clumsy procedure refined in the water tank made the final design exponentially more robust. This phase transformed the project from a collection of brilliant ideas into a portfolio of proven technologies. The confidence it built was tangible, moving the mission from a calculated gamble to a foreseeable reality. The theoretical solutions painstakingly developed on computer screens were now validated by physical law, having survived their trial in the simulated crucible of space. With the prototypes perfected and the blueprints updated with hard-won knowledge, the focus could finally shift from testing models to forging the real thing, initiating a global hunt for the raw materials and manufacturing prowess needed to build humanity's first factory among the stars. Procuring the raw ingredients for this orbital endeavor was a logistical puzzle spanning the entire globe, a silent symphony of coordination that turned the planet itself into a foundry for the stars. Every single component, from the largest structural beam to the tiniest microchip, had to be scrutinized not just for its function, but for its ability to survive two of the most violent journeys imaginable. First, the brutal, shaking ascent atop a controlled explosion, and second, a permanent existence in the silent, punishing vacuum of space. The mantra for material selection was ruthless efficiency, lightweight, high strength, and radiation resistant. This ruled out most conventional materials immediately. Instead, the supply chain came to rely on advanced carbon fiber composites, marvels of engineering that are feather-light yet stronger than steel, and exotic titanium, aluminum, vanadium alloys specifically formulated to resist the embrittling effects of cosmic radiation over decades. Even the paints and coatings were special, formulated to reflect solar heat and protect against the relentless ultraviolet light that degrades conventional materials. While the initial construction would rely entirely on materials launched from Earth, the long-term vision always pointed toward self-sufficiency. This led to fascinating and forward-thinking partnerships with mining and resource extraction companies. Teams of planetary geologists and engineers began seriously studying the feasibility of using in situ resources, a technical term for using what's already out there. They ran detailed analyses on lunar regolith, the dusty soil covering the moon, developing prototypes for processes that could melt it into construction materials or extract vital oxygen and water ice. Even more ambitious were the plans for asteroid mining, targeting nearby metallic asteroids that are essentially flying mountains of iron, nickel, and precious metals like platinum and cobalt. The goal was to eventually build an entire supply chain in space, where raw materials are harvested from asteroids or the moon, processed at an orbital depot, and then shipped to the factory, drastically reducing the astronomical cost and environmental impact of launching everything from the bottom of Earth's gravity well. These partnerships, though focused on the future, were crucial for developing the technologies that would one day make the factory truly independent. Back on Earth, turning these specially sourced materials into flight-ready components required manufacturing techniques that felt like science fiction themselves. Additive manufacturing, or large-scale 3D printing, became a cornerstone of the production process. Entire sections of the factory's truss and complex mounting brackets were printed as single, seamless units, a method that created incredibly strong, lightweight structures with almost zero material waste compared to traditional machining that carves away 90% of a solid block. For the most sensitive components, like optical sensors and certain electronics, they employed atomic layer deposition. This incredibly precise technique builds materials one atom at a time, allowing engineers to create perfect nanoscale coatings that could protect a surface from corrosion, manage its electrical properties, or make it incredibly slippery. This level of control was essential for creating the flawless surfaces needed for certain manufacturing processes in space. Before any part could earn its ticket to orbit, it had to run a gauntlet of some of the most stringent quality control procedures ever devised. Each piece was given a serial number and a digital passport that tracked its entire life cycle, from the mine where its ore originated to the final installation in space. It was subjected to violent shake tests that simulated the intense vibrations of a rocket launch, ensuring nothing would crack or come loose. It was baked in ovens and frozen in cryogenic chambers, cycled through extreme temperatures hundreds of times to test for expansion, contraction, and fatigue. It was bombarded with radiation in particle accelerators to simulate years of exposure in a matter of days. Any component that showed the slightest weakness, even a microscopic crack or an unexpected change in electrical conductivity, was rejected immediately. The philosophy was simple and uncompromising. There are no hardware stores in space. Every single item had to work perfectly the first time and for years thereafter. The final challenge was a masterpiece of logistical optimization. Logistics experts had to become masters of a four-dimensional puzzle, coordinating the production schedules of hundreds of suppliers across the world with the limited and expensive launch windows on rockets from multiple different companies. Their goal was to have components arrive at the launch site just in time for integration, avoiding costly storage delays, while also packaging everything with insane efficiency to use every single cubic inch of precious payload space. They designed custom folding and nesting mechanisms for large items like solar panels, allowing them to be packed as densely as a piece of origami and then unfold automatically in orbit. They worked with launch providers to understand the specific vibration and G-force profiles of each rocket type, tailoring the cushioning and support structures inside the payload fairings to protect their delicate cargo. This phase was a powerful testament to human collaboration, a silent global effort where a precision gear forged in Germany, a radiation-shielded circuit board assembled in Japan, and a composite panel molded in California all converged at a launch pad in Florida, each a vital piece of the grandest puzzle ever attempted. This global skeleton, now complete and tested, was ready for its final and most dramatic journey, a fiery ascent out of Earth's embrace and into the waiting darkness of space. This phase of the project was a breathtaking symphony of fire and physics, a carefully orchestrated campaign that saw the factory's components begin their slow, deliberate migration from Earth's surface to their waiting orbital slots. It was a logistical endeavor unlike any other, relying on a diverse fleet of reusable rockets from pioneering companies like SpaceX, with its iconic Falcon boosters landing themselves on drone ships, Rocket Lab, recovering their smaller Electron rockets mid-air with helicopters, and Blue Origin with their new Glenn heavy lift vehicles. This wasn't about choosing one provider. It was about creating a resilient and flexible launch manifest, ensuring that a delay or issue with one company wouldn't bring the entire project to a grinding halt. Each launch provider brought unique strengths to the table, allowing the team to match the specific rocket to the specific module, sending heavier, denser components on the larger vehicles and more delicate, specialized equipment on the smaller, more nimble rockets that could offer a gentler ride. The timing of each launch was a masterclass in celestial mechanics, a dance dictated by the unyielding laws of orbital dynamics. Launch windows weren't just a matter of good weather at the Cape. They were calculated down to the second to ensure each module would arrive at the precise orbital altitude and inclination needed for the eventual assembly. Teams of orbital planners used sophisticated software to plot trajectories that would avoid not only bad weather and high-altitude winds, but also the ever-growing cloud of space debris and active satellites, turning Earth's orbit into a carefully managed highway system. A launch delayed by even a few minutes could mean waiting days or weeks for the next available window where all these complex factors aligned, turning the launch schedule into a high-stakes game of precision scheduling where billions of dollars and years of work were on the line with every countdown. Perhaps the most ingenious engineering feat was the packaging of the modules themselves. These were not simply boxes loaded onto a rocket. They were masterpieces of geometric efficiency and robotic origami. Every conceivable inch of space inside the rocket's payload fairing was utilized. Solar panels were folded into compact, layered stacks, like a masterfully crafted paper fan. Delicate robotic arms were curled into tight, protective coils. The central truss segments were designed to nest perfectly inside one another. Each module was equipped with a suite of tiny but incredibly reliable mechanisms, pyrotechnic bolts, shape memory alloys, and slow-release tendons, all designed to initiate a complex, automated unfolding sequence once the module was safely released into the vacuum of space. This deployment was triggered by a simple, on-command from mission control, beginning a silent, balletic transformation where a dense, compressed cube would gradually unfurl into a sprawling, functional piece of the factory, its solar arrays stretching out like wings to greet the sun. The public spectacle of these launches played a crucial role in the entire endeavor. Nearly every launch was live streamed in high definition, transforming a technical milestone into a global event that captured the world's imagination. Millions watched from their homes as columns of fire pushed against the gravity of a planet, as boosters separated with perfect, explosive precision, and as the second stages ignited to carry their precious cargo the final stretch into the blackness of space. These were not just promotional tools, they were a powerful statement of transparency and inclusion, making every citizen a virtual witness to the birth of a new era. The sight of a rocket booster descending gracefully back to a landing pad, its own engines firing to slow its fall, became a symbol of the new, sustainable economics of spaceflight, proving that access to orbit was becoming routine and affordable. Yet, behind the public triumph was a relentless focus on risk mitigation. For every primary launch vehicle on the manifest, an identical backup rocket was being prepared on a parallel track, often at a different launch site across the country or the world. This redundancy was the project's insurance policy. If a rocket suffered a technical fault that delayed its launch, or worse, if a launch failed and a module was lost, the backup vehicle could be rolled out to the pad on an accelerated schedule. The modules themselves were also designed with redundancy in mind. For all but the most unique components, there was often a second, identical unit built and in storage, ready to be called up if its twin was lost. This layered approach to ensuring continuity meant that no single rocket explosion, no one failed deployment, could spell the end for the orbital factory. It was a philosophy that acknowledged the inherent danger of spaceflight while systematically engineering around every possible point of failure. The culmination of each launch was a moment of intense, quiet celebration in mission control. The successful deployment of a module from the rocket's upper stage, confirmed by the first telemetry signals received at a ground station, marked the end of a fiery journey and the beginning of a peaceful orbital existence. Each new signal was a triumph, not just of the launch providers, but of the thousands of engineers who had designed, tested, and built that component to survive the ordeal. With each new module safely in its predetermined orbital slot, the celestial chessboard slowly gained its pieces, setting the stage for the most delicate and complex phase of the entire project, the intricate robotic ballet of connecting these disparate parts into a single, cohesive, and functioning whole. The quiet void of space became a bustling construction site, a silent symphony of autonomous machinery choreographed with breathtaking precision from over 200 miles below. The assembly phase was a delicate, months-long dance where every movement had to be calculated to account for the fundamental strangeness of orbital mechanics. On Earth, building something is largely a battle against gravity. You stack things up and they mostly stay put. In orbit, the primary challenge is managing momentum. Every action, no matter how small, has an equal and opposite reaction. The gentle push of a robotic arm extending could impart a slight spin to the entire structure. A bolt being tightened could send tiny shockwaves through the framework. To combat this, the assembly robots were equipped with incredibly sensitive force-torque sensors and an array of tiny, cold gas thrusters. After performing any task that imparted force, they would fire these micro-thrusters in the opposite direction, cancelling out the movement and holding the entire growing factory in perfect, stable equilibrium. It was a constant, silent conversation between action and reaction, happening dozens of times every minute. Guiding this ballet were the teams on Earth, but they weren't driving the robots like remote-controlled cars. The time delay of even a few seconds for signals to travel up and down made direct teleoperation impossible. Instead, they worked through a sophisticated layer of supervisory control. Engineers in mission control would designate a high-level goal, Dock Module Gamma to Port 4, and the on-site AI, fueled by a torrent of real-time telemetry data, would then compute the thousands of tiny, precise movements needed to achieve it. The AI would execute the maneuver, constantly checking its progress against the predicted path and pausing instantly if anything deviated even a millimeter from the plan. Human operators watched over the AI's shoulder, so to speak, monitoring complex visualizations of force, alignment, and structural stress. Their role was to approve each major step, troubleshoot anomalies, and make strategic decisions while the AI handled the intricate, real-time physics. This partnership leveraged the raw computational power and unwavering precision of machines with the nuanced intuition and big-picture reasoning of human beings. The eyes of the operation were an array of advanced computer vision systems, high-resolution cameras, LiDAR scanners, and laser rangefinders coated every surface of the assembly robots and the modules themselves. These didn't just provide a video feed, they created a live, three-dimensional map of the entire worksite, updated millisecond by millisecond. As a robotic arm maneuvered a massive solar array into position, the vision systems were constantly measuring the gap between the docking ports, calculating the angles of approach, and verifying alignment down to a fraction of a millimeter. They could detect a misalignment invisible to the human eye and signal the arm to make a microscopic correction long before any metal touched metal. This was crucial for tasks like connecting fluid and electrical umbilicals, where a misaligned pin could bend or break, jeopardizing the entire connection and creating a potential source of failure that would be incredibly difficult to repair. While the assembly was predominantly robotic, there were moments that demanded the deft touch of a human hand. This is where the residents of the International Space Station and other fledgling orbital outposts came in. On several occasions, crews would travel via their spacecraft to the construction site for what were termed assembly and verification missions. Their roles were multifaceted. They performed detailed, hands-on inspections of critical connections, using specialized tools to verify torque settings on bolts that robots had installed. They deployed external wiring harnesses and routed flexible coolant lines, tasks that required a level of manual dexterity and problem-solving in a bulky spacesuit that still eluded even the most advanced robots. They also served as the ultimate contingency plan. During the installation of the primary command module's external observatory window, a protective cover failed to deploy as intended. Within hours, a two-person crew was on site. Working carefully, one astronaut manually released the cover while their partner documented the procedure, providing invaluable data for engineers to improve the design for future modules. These human interventions were not signs of failure but rather a brilliant design feature, a recognition that the flexibility and adaptability of a human in the loop were irreplaceable assets for such a complex endeavor. Looming over every aspect of the assembly was an invisible, high-speed threat, orbital debris. The factory's orbit was carefully chosen to be in a relatively clean corridor, but the risk of a catastrophic collision with even a tiny screw traveling at 17,000 miles per hour was ever present. The assembly AI was in constant communication with global space surveillance networks, receiving regular updates on the trajectory of known debris objects. If a piece of tracked debris was predicted to pass within a predetermined safety margin, the entire assembly process would automatically pause. The factory's own suite of thrusters would then fire, nudging the entire structure slightly out of the way in a maneuver called a debris avoidance burn. After the all-clear was given, the thrusters would fire again to return to the precise orbital position needed to continue construction, a testament to the incredible navigational precision required to build in such a dynamic environment. As the months passed, the disconnected collection of modules and trusses slowly, painstakingly, evolved into a recognizable shape. The central spine was completed, a long, backbone-like structure bristling with attachment points. The habitat and command modules were docked, their windows staring out into the infinite black. The massive solar arrays were unfolded and connected, their vast, dark blue surfaces slowly tilting to track the sun. Each new connection was a milestone celebrated in mission controls around the world. The assembly phase was a monumental demonstration of patience, precision, and international cooperation. It proved that we could not just visit space, but truly build there, creating permanent, complex infrastructure piece by piece. With the final structural element locked into place and the last bolt torqued to perfection, the factory was whole. It now existed as a single, integrated structure, silent and waiting. The hard part was over. Now it was time to wake it up. With the final module securely in place and the factory's skeletal structure complete against the star-dusted blackness of space, the most delicate phase of the entire endeavor began. This was not about construction, but about awakening. The facility was a dormant giant, and the process of powering it up was a meticulously choreographed sequence, more akin to bringing a patient out of a deep coma than flipping a simple switch. The absolute priority was the factory's heart and nervous system, its core computing and communication arrays. Without these, the entire structure would be a blind, deaf, and brainless shell. Engineers on Earth sent the first activation command, a digital whisper traveling at the speed of light. Across the void, a trickle of power from internal batteries flowed into the main servers. One by one, status lights on control panels flickered from dark to a steady, reassuring green. The factory had begun to think. It established its first tentative link with mission control, a thin thread of data confirming it was alive and listening. This initial trickle of energy was just the beginning. The factory's lifeblood would come from its expansive solar arrays, which now began their own automated unfurling sequence. Like the wings of a colossal mechanical butterfly, the arrays extended, their dark blue photovoltaic cells orienting themselves toward the sun. As they drank in the raw, unfiltered sunlight, a surge of power began flowing into the system. But sunlight in low Earth orbit is an intermittent resource. Every 45 minutes, the factory would plunge into the Earth's shadow for a period of orbital night, a total eclipse that could last up to 36 minutes. To survive these regular blackouts, the factory relied on massive lithium-ion battery arrays, the largest ever deployed in space. These banks stored the surplus energy generated during the sunlit periods, creating an essential reservoir that would keep every critical system running seamlessly through the darkness, ensuring there was never a flicker or a moment of downtime. Yet, for the intense energy demands of heavy manufacturing, melting metal alloys, running industrial furnaces, and powering banks of supercomputers, solar power and batteries alone presented a challenge. This is where a truly revolutionary technology came into play: experimental compact fission reactors. These were not the massive nuclear plants of Earth, but small, sealed, and incredibly safe units designed to provide a constant, reliable base load of power, utterly independent of the sun. They acted as the factory's unwavering industrial heartbeat, generating steady power through all phases of its orbit. Their activation was the most nerve-wracking procedure of the entire power-up sequence. Teams of nuclear engineers and robotic specialists oversaw the automated startup from their consoles, monitoring neutron flux and coolant loop temperatures with bated breath. The successful, stable operation of these reactors was a monumental achievement in itself, proving that safe, compact nuclear power could sustain long-term industrial activity beyond our planet. With a stable and abundant power supply now confirmed, The activation sequence could proceed to the systems that would make the factory a livable, workable environment. Next came the environmental controls, the facility's lungs and circulatory system. Engineers commanded the startup of the vast, closed-loop air revitalization system. Giant fans whirred to life, beginning the constant circulation of atmosphere. Carbon dioxide scrubbers activated, using advanced crystalline materials to pull exhaled CO2 from the air. Electrolyzers then split that captured CO2, reclaiming precious oxygen and even creating a small supply of methane fuel as a byproduct. Similarly, water recovery systems began their endless cycle, purifying every drop of moisture from the air and any wastewater through a series of filters and distillation chambers, achieving a near-perfect 98% recycling rate. The hum of these life-giving machines was the sound of the factory beginning to breathe. The power management itself was a masterpiece of artificial intelligence. Sophisticated algorithms constantly monitored energy production from the solar arrays, the steady output of the reactors, the storage level of the batteries, and the real-time demand from every corner of the factory. This smart grid could make split-second decisions, dynamically routing power to where it was needed most. If a manufacturing furnace began a high-energy melt cycle, the system could temporarily reduce non-essential power to lighting in uninhabited modules or delay a non-critical battery recharge cycle. It was a self-aware, self-optimizing nervous system for power, ensuring not a single watt was wasted, and that critical systems like communications, computation, and life support were always prioritized above all else. Each system activation was a milestone met with quiet relief in mission control. There was no single moment of celebration, but rather a slow, building wave of confidence as each redundant subsystem reported a perfect status. The power grid was not just online, it was robust, intelligent, and resilient. It had survived its first orbital eclipses without a hiccup, seamlessly switching between solar, battery, and nuclear sources. This successful boot-up was far more than a technical box-ticking exercise. It was the ultimate proof of concept that sustained, complex, and power-intensive operations were not only possible in space, but could be managed with an elegance and efficiency that rivaled the most advanced facilities on Earth. The factory was no longer just a structure, it was a fully functional vessel, alive with energy and waiting for its purpose. The stage was now set, the tools were powered, the environment was stable, and the entire world was watching. The moment had finally arrived to answer the fundamental question that had launched this endeavor years before. Could this factory actually build something? The moment of truth arrived not with a dramatic countdown, but with a series of silent, digital commands sent from a control room on Earth. The factory's inaugural manufacturing run was a carefully chosen mission designed for a high-probability, high-impact success. The product was deceptively simple, a batch of silicon crystals, the fundamental building block of all modern electronics, but these were not meant to be ordinary crystals. On Earth, gravity is the enemy of perfection in this process. As molten silicon cools and solidifies, convection currents, those swirling movements within the liquid caused by heat rising and coolness sinking stir in impurities and create microscopic stresses and defects in the crystal's atomic lattice. These tiny flaws are the reason our most advanced computer chips still generate immense heat and hit performance ceilings. In the persistent, gentle free fall of microgravity, those chaotic currents simply vanish. The molten silicon could cool in a state of perfect equilibrium, allowing atoms to arrange themselves into an immaculate, uniform structure, a flawless lattice that theorists had dreamed of for decades. The entire process was a ballet of autonomous precision. Robotic arms, their movements calibrated to the millimeter, retrieved a sealed cartridge of ultra-pure silicon from a storage rack. They placed it with infinite care into a cylindrical growth chamber, a sophisticated furnace whose temperature could be controlled to within a fraction of a degree. A seed crystal, a tiny, perfect piece of silicon that acts as a template, was lowered into the molten silicon soup. Then, with painstaking slowness, it was withdrawn, drawing the molten material up with it, atom by atom, to extend the crystal's perfect structure. This delicate operation, which on Earth requires constant human adjustment to counteract gravity's distortions, here ran entirely on pre-programmed instructions, the robots executing their tasks with an unwavering steadiness impossible for any human hand. Throughout the days-long process, the factory itself became a sentient observer. A network of sensors embedded in the growth chamber provided a constant stream of data back to eager engineers on Earth. They monitored thermal gradients with infrared cameras, tracked pressure levels, and used X-ray diffraction to peer directly into the growing crystal's atomic structure without ever touching it. This real-time telemetry was like watching a masterpiece being painted in ultra-slow motion, with every brushstroke visible. The controllers on the ground could watch the flawless lattice forming, a digital confirmation that the theory was holding true in practice. There was no need for intervention. The system was performing exactly as designed, a testament to the years of prototyping and simulation that had led to this moment. When the growth cycle was complete, the robotic arms moved in again. They carefully extracted the finished crystal cylinder, now several centimeters in diameter and over a meter long, and transferred it to an imaging station for a full structural analysis. The data that scrolled across the screens in mission control was nothing short of breathtaking. The crystal was not just good, it was orders of magnitude more perfect than any ever produced on Earth. It exhibited virtually none of the dislocations or impurities that plague terrestrial crystals. Its electrical properties were so superior that chips made from it would theoretically run cooler, faster, and far more efficiently, potentially unlocking new generations of computing power and dramatically reducing the energy consumption of vast data centers worldwide. The successful production of that first flawless silicon ingot was far more than a technical milestone. It was the entire justification for the Orbital factory made manifest. It validated the core business case and the fundamental physics that had driven the Visionaries for half a century. This was no longer an abstract concept or a promising simulation. It was a tangible, valuable product, physically floating in a module overhead, that proved beyond any doubt the economic and scientific value of manufacturing in space. That first batch of crystals provided the essential blueprint, the proven playbook for operating the factory's systems in a real production environment. It gave engineers the confidence to move from a single, carefully managed test to planning for continuous, scaled-up production. More importantly, it shattered psychological barriers, demonstrating that the immense complexity and cost of the endeavor could yield a material return. With this undeniable proof of concept securely in hand, the project's focus could now confidently expand beyond this one triumphant experiment to unlock the factory's full, multifaceted potential. The triumph with silicon crystals was merely the opening act, proving the foundational principle that microgravity could unlock new levels of material perfection. With that confidence surging through the teams on the ground, the Orbital factory's mission rapidly expanded, transforming from a specialized workshop into a breathtakingly versatile industrial platform. The next phase was a deliberate and thrilling exploration of its full potential, testing processes across wildly different fields to see what other miracles the unique environment of space could perform. This wasn't just about making one thing better, it was about discovering entirely new things that were previously impossible to make at all. one of the most emotionally resonant experiments began in a module dedicated to biological sciences. Here, the focus shifted from inorganic crystals to the very building blocks of life. The process is known as bioprinting, a technology that exists on Earth but is fundamentally hampered by gravity. On the ground, 3D printers attempt to construct delicate, living tissues by layering bioinks, gels filled with living cells. But these soft, watery structures are fragile, and the weight of each new layer can compress and collapse the delicate, intricate architecture of the ones below, particularly when trying to create complex vascular networks that mimic blood vessels. In the persistent free fall of orbit, that crushing force simply disappears. The bioinks hold their shape perfectly, allowing printers to meticulously construct tissue samples with a structural integrity and cellular uniformity that was previously unattainable. The factory's first batches of cardiac tissue didn't just look like heart muscle under a microscope. They behaved like it, twitching and beating in a synchronized rhythm that left researchers watching the video feeds in awe. This wasn't just a lab sample, it was a potential revolution. It promised pharmaceutical companies a perfectly accurate human tissue model for testing new drugs, eliminating the inaccuracies of animal testing. And further down the line, it illuminated a path toward the holy grail of medicine, the ability to print entire, viable organs for transplantation, potentially ending the agonizing waitlists that cost thousands of lives every year. In another part of the facility, the focus was on brute strength rather than biological delicacy. The alloy manufacturing modules became a forge for the future of transportation and exploration. On Earth, when you try to mix certain metals to create a new, stronger alloy, a frustrating thing happens. Heavier elements sink while lighter ones rise, creating an inconsistent mixture that weakens the final product. This is why some theoretically super-strong alloy combinations have remained laboratory curiosities. They can't be mixed uniformly under gravity's influence. In the factory's microgravity furnaces, this fundamental barrier vanished. Metals with vastly different densities could be melted together, and they would stay perfectly blended, like a smooth emulsion instead of a separating salad dressing. The results were metallic composites that seemed to defy conventional material science, alloys that were as light as aluminum but possessed the strength and heat resistance of high-grade titanium. Aerospace engineers immediately saw the potential. Every kilogram saved on an airframe or a spacecraft fuselage translates to massive fuel savings and greater payload capacity. These space-forged alloys promise to make the next generation of aircraft significantly more efficient and environmentally friendly, and to enable spacecraft that could travel farther and carry more into the solar system. Simultaneously, a quieter but equally transformative process was underway for the communications industry. The production of fiber optic cable, the glass threads that form the backbone of the global internet, has always been a battle against imperfection. Even microscopic impurities or tiny bubbles trapped within the glass as it's drawn into a thin strand can scatter light signals, causing attenuation, a gradual weakening of the signal that requires booster stations every 50 miles or so to keep data moving. In the vacuum environment of the Orbital factory, the drawing of fiber optic strands was a pristine process. With no air to create bubbles and no contaminants to introduce impurities, the factory could produce kilometers of perfectly clear, flawless glass fiber. The light signals traveling through these space made fibers exhibited dramatically less signal loss, meaning they could travel vastly greater distances without needing a boost. This had the potential to revolutionize global communications, making undersea cables more efficient and reliable, and even enabling high-speed data networks in remote and underserved regions of the world by reducing the infrastructure needed to support them. Each of these new product lines demanded intense customization. The modular design of the factory, a core principle from those very first conceptual blueprints, now proved its worth. Adding a bioprinter wasn't a massive retrofit. It was a matter of docking a new, specialized pod to the central spine, one that contained its own sterile environment and precise robotic handlers. Retooling for a new alloy mixture meant swapping out a furnace module and updating the software protocols for the robotic arms. This plug-and-play philosophy allowed the facility to pivot between radically different industries with an agility that would be unimaginable in a terrestrial factory. This rapid iteration was supercharged by the project's partnerships. Major pharmaceutical corporations provided the cells and bio-inks for the tissue experiments, while aerospace giants supplied the raw metals for the alloy forges. Their deep domain knowledge, combined with the factory's unique capabilities, created a powerful feedback loop of innovation. The high demand for even the initial batches of these space-made goods from these partners provided undeniable proof of economic viability. The Orbital factory was no longer a speculative venture. It had become a profitable multi-industry hub, its production schedule booked months in advance by companies desperate for a competitive edge. This explosive growth and diversification, however, brought a new level of operational complexity that could only be managed by handing over the reins to a new kind of intelligence. Managing this explosion of diverse and complex production lines would have been utterly impossible with human oversight alone. The sheer volume of decisions, from scheduling which high-value product to manufacture next to predicting when a pump might fail, required a level of speed and data crunching power that only artificial intelligence could provide. The factory's digital brain evolved from a simple management tool into a truly cognitive partner, an omnipresent intelligence woven into every circuit and every system. This was not about replacing human ingenuity, but about augmenting it, freeing the brilliant minds on Earth to focus on creative problems and strategic leaps, while the AI handled the millions of micro-decisions needed for day-to-day perfection. At the heart of this system were incredibly sophisticated machine learning algorithms that acted as the facility's chief operating officer, logistics coordinator, and head of maintenance, all rolled into one. These algorithms were constantly digesting a fire hose of data, real-time power consumption from every module, the precise completion status of a crystal growth run, the spectral purity of a newly drawn fiber optic strand, even the subtle vibration signatures of every pump and motor. With this information, the AI could perform miracles of optimization. It could dynamically reschedule the entire factory's production queue in milliseconds if a solar flare threatened to cause a temporary power dip, shifting energy-intensive alloy forging to a later time and prioritizing lower-power bioprinting tasks instead. It learned the unique energy and material footprints of every single process, finding ways to minimize waste with an efficiency no human planner could ever match, like scheduling the waste heat from a cooling furnace to pre-warm a module that needed a temperature boost. This predictive capability extended into the realm of maintenance, transforming it from a reactive chore into a graceful, preemptive ballet. The AI's neural networks were trained on thousands of simulated failure scenarios and years of data from the International Space Station. They became incredibly adept at spotting the faintest whispers of impending trouble long before any human operator would notice a red light on a console. By analyzing the subtlest changes in the harmonic resonance of a fan blade or a minute deviation in the current draw of a servo motor, the system could flag a component for servicing weeks before it was likely to fail. This allowed for repairs to be scheduled at the most convenient time, often performed autonomously by the factory's own robotic custodians, utterly avoiding the catastrophic downtime a sudden breakdown would cause in such a remote and fragile environment. These robotic systems were the physical hands of the AI's will. They evolved far beyond the pre-programmed arms used in initial assembly. Equipped with advanced computer vision and sensitive force feedback sensors, they became true generalists. One day, a robot might be delicately manipulating a cartridge of human stem cells into a bioprinter with the steady care of a master surgeon. The next, the same robot could be using a cutting torch to replace a section of coolant pipe, then switching tools to conduct a precise ultrasonic weld inspection. They learned from each other, sharing data across the network so that a repair procedure perfected by one robot in the alloy module was instantly available to all the others, creating a hive mind of mechanical expertise that grew smarter and more capable with every task it completed. For the human engineers back on Earth, interacting with this complex artificial organism needed to be intuitive, not a chore of memorizing thousands of obscure command lines. This led to the development of incredibly natural language interfaces. A flight controller could simply ask aloud, "What's the current yield efficiency on the semiconductor run in Module 2?" And the AI would not only recite the number but also pull up relevant trend graphs and offer a conversational analysis of any anomalies. More impressively, they could issue complex commands in plain English. Please prioritize the cardiac tissue batch and have the maintenance bot in Hub 4 run a diagnostic on the air scrubber after it finishes its current task. The AI would understand the intent, context, and priorities, then translate that casual instruction into a perfect sequence of machine code and execute it flawlessly. This seamless collaboration slashed the decision-making latency that would have been caused by waiting for human input on every minor issue, creating a resilient, adaptive system that could handle unexpected events. A sudden debris avoidance maneuver, a temporary communications blackout with calm, autonomous efficiency. In many ways, the Orbital factory became the most advanced testbed for autonomous industrial operations ever created, a proof of concept that was generating priceless insights for factories back on Earth. The algorithms developed to manage a closed-loop system in space, where every watt and every drop of water is precious, were being adapted to create hyper-efficient smart grids and manufacturing plants across the globe. The predictive maintenance models were revolutionizing how airlines service their jets and how power plants manage their turbines. The success of this orbital AI wasn't just about building better products in space. It was about sending a continuous stream of innovation back home, improving efficiency and sustainability for industries worldwide. This deep, seamless fusion of human and machine intelligence created a robust and resilient operational foundation, proving that such a complex system could not only function but thrive on its own. This newfound autonomy was the essential prerequisite for the next evolutionary step, one that would bring the human element back into the loop in a more intimate and powerful way than ever before. Even with its incredibly sophisticated artificial intelligence humming along perfectly, the factory was never truly alone. A constant, silent conversation flowed between its orbiting modules and a network of mission control centers scattered across the planet, creating an unbreakable tether of data and human vigilance. This was the crucial hybrid model in action, a perfect partnership where the AI's lightning-fast precision was seamlessly blended with the nuanced judgment, creativity, and instinct of human experts. Teams of specialists worked in shifts, ensuring that every single manufacturing process, every system heartbeat, and every external condition was monitored 24 hours a day, 7 days a week. These weren't just passive observers watching screens, they were active conductors of a celestial orchestra, their consoles providing a living dashboard of the factory's health and productivity. This persistent human connection was the project's ultimate safety net, a layer of oversight that could handle the truly unexpected, the anomalies and edge cases that no amount of simulation could have ever predicted. The interface between these human controllers and the distant factory was something straight out of science fiction, designed to collapse the 200-mile gap and make the experience feel profoundly intuitive. Engineers didn't just look at data on a screen, they stepped inside the factory through the lens of virtual reality. Donning advanced VR headsets, a specialist could be instantly transported to the interior of a specific module, seeing a photorealistic, three-dimensional recreation built from live camera feeds and sensor data. They could float right up to a crystal growth furnace to inspect a readout or circle a bioprinter to examine its progress from every angle. This visual immersion was then combined with the miracle of haptic feedback. Using specialized gloves and robotic interfaces, an engineer could reach out and actually feel the equipment they were seeing in the virtual space. They could sense the resistance of a virtual valve as they turned it, feel the subtle vibration of a pump motor through their fingertips, or even experience the weight and texture of a virtual tool. This multi-sensory connection transformed complex remote procedures from an abstract series of commands into a tactile, intuitive experience, drastically reducing the mental load and the potential for error. Beneath this immersive layer existed a relentless, invisible river of raw information. Thousands of sensors embedded throughout the factory generated a continuous torrent of data: temperature readings, pressure levels, power flows, spectral analyses of manufactured goods, and even the minute vibrational signatures of every spinning fan and pump. This colossal data stream was funneled down to Earth, where it was ingested by powerful machine learning algorithms, acting as a first line of defense. These algorithms were trained to recognize the digital fingerprint of normal, healthy operation. Their sole job was to constantly sift through the noise, watching for the faintest whisper of an anomaly, a temperature reading that deviated by half a degree from its predicted path, a power draw that exhibited a strange, tiny fluctuation, or a communication latency that was a few microseconds too long. When they detected something out of the ordinary, they didn't sound a general alarm. Instead, they performed a triage function, instantly flagging the specific issue and routing it directly to the human specialist most qualified to handle it, complete with a prioritized recommendation and relevant context pulled from the historical database. This allowed the human experts to focus their precious attention on solving problems, not on the exhausting task of searching for them. This continuous dialogue wasn't just about monitoring and repair, it was also about growth and evolution. The factory's software was never static. Just like the smartphone in your pocket, it received regular updates beamed up from Earth. These weren't just bug fixes, they were capability enhancements. A team of software developers might perfect a new algorithm for more efficient battery charging based on months of operational data, and that new code could be transmitted overnight, making the entire facility smarter while it slept. Security patches were a constant priority, fortifying the factory's digital walls against any potential threat in an increasingly complex orbital landscape. These updates ensured that the facility was constantly learning and improving, its performance ascending to new heights long after its physical construction was complete. This ability to remotely upgrade and refine the entire operation was a game-changer, proving that an orbital facility could adapt and evolve without ever needing a physical visit, fundamentally altering the economics and longevity of such projects. The breathtaking success of this remote oversight model did more than just keep the factory safe. It fundamentally rewrote the blueprint for how humanity would operate in space. It proved that we could build, manage, and continuously improve immensely complex industrial systems far from our home planet, all while keeping human operators safely on the ground for the vast majority of routine tasks. This dramatically reduced the risk and cost associated with maintaining a permanent human presence in orbit, as crews would no longer be needed for every minor adjustment or repair. The lessons learned in managing latency, processing immense data streams, and creating intuitive human-machine interfaces were immediately adopted by other industries, from deep-sea robotics to remote surgery. Most importantly, it built the essential confidence that such a venture was not only feasible but sustainable for the long term. This proven capability to manage the factory flawlessly from a distance was the final piece of the puzzle that made the next logical step not just possible, but inevitable: the careful, calculated introduction of a human crew to bring their unique abilities directly into the orbital workspace. Despite the flawless execution of its autonomous systems, the orbital factory's evolution reached a pivotal new chapter with the arrival of its first human inhabitants. These weren't astronauts in the traditional, exploration-focused sense. They were highly specialized technicians, the first of a new profession we might call orbital industrial engineers. They traveled not on government-owned capsules, but aboard sleek, commercial spaceplanes operated by companies like SpaceX and Sierra Space, vehicles that were now making routine taxi flights to low Earth orbit. Their journey from Earth was a stark contrast to the violent, explosive ascent of the factory's modules. It was a smooth, almost airline-like experience, a testament to how rapidly access to space was becoming normalized. Stepping through the docking port for the first time, these pioneers didn't just enter a workplace. They crossed a threshold into a new way of living and working for humanity. Their new home was a dedicated habitat module, a marvel of ergonomic design and psychological support. Every inch was optimized for efficiency and well-being in a world without up or down. Handrails and foot restraints were strategically placed for easy movement, and workstations could be reconfigured for any orientation. The air carried the faint, clean scent of recycled atmosphere, a constant hum from the life support systems providing a reassuring backdrop of mechanical life. But it was the windows that truly defined the experience. Large, panoramic viewports offered a breathtaking, ever-changing vista of our planet rolling by below, swirling white clouds over deep blue oceans, the glittering lights of cities at night, and the profound blackness of space punctuated by countless stars undimmed by atmosphere. This wasn't just a scenic bonus, it was a crucial psychological anchor, a daily reminder of the world they were working for and the incredible vantage point from which they were serving it. The tasks that demanded their presence were those that still eluded even the most advanced robotics. Problems requiring fine motor skills, nuanced judgment, and creative improvisation. A robotic arm might be perfectly programmed to replace a standard component, but when a sensitive optical calibrator, essential for monitoring crystal growth, was knocked out of alignment by a minor debris impact, it took a human touch. A technician, anchored in place, could use specialized tools to perform microscopic adjustments, their hands guided by years of experience and an intuitive feel for the machinery that no algorithm could replicate. They conducted experiments that required real-time observation and adaptation, like refining a bioprinting process by visually assessing the structural integrity of a tissue sample and making on-the-fly adjustments to the printer's parameters. Their most valuable role was often as troubleshooters for the robotic systems themselves. When a mobile maintenance bot began behaving erratically, instead of following a lengthy remote diagnostic procedure, a technician could simply float over, open an access panel, and visually identify a loose connection or a worn gear, fixing it in minutes rather than hours. Life on board settled into a unique rhythm that blended intense, focused work with moments of profound wonder. Their schedules were rigorous, broken into shifts that coordinated with mission control teams on the ground. They held daily planning conferences via video link, reviewing the task list and discussing any anomalies. Meals were not just for nutrition but were vital social events, a time to share findings, decompress, and maintain camaraderie in an environment that could otherwise feel isolating. The food itself was a testament to advancement far from the paste-like tubes of early spaceflight. It included rehydratable gourmet meals and even fresh fruits and vegetables occasionally delivered on resupply missions, a tiny taste of Earth that provided a massive morale boost. In their off hours, they would often gravitate towards the windows, sharing the awe of a sunrise that occurred 16 times a day, or pointing out landmarks to each other on the globe below. These moments of shared wonder were not leisure. They were essential for mental health, reinforcing the profound purpose of their mission. The impact of this human presence was immediate and transformative, adding a layer of flexibility and creative problem-solving that pure automation could never achieve. Innovation accelerated dramatically. A technician watching a manufacturing process might notice a subtle inefficiency, a robotic arm taking a slightly awkward path, or a cooling system cycling on and off too frequently, and suggest a simple software tweak that saved energy and time. They could perform small-scale, impromptu experiments, testing a new tool or a different material sample without needing to program an entire robotic sequence from Earth. This synergy between human and machine created a feedback loop of continuous improvement. The AI handled the predictable, repetitive, and data-intensive tasks with flawless precision, while the human crew handled the unpredictable, the novel, and the intuitive. They became the factory's hands, eyes, and conscience, a living extension of the intelligence that built it. Their successful integration proved that the future of space industry wasn't a choice between humans and robots, but a powerful partnership that leveraged the unique strengths of both. As these crewed rotations became a regular, almost routine part of operations, the focus naturally expanded from merely operating the factory to ensuring it could thrive and grow indefinitely, turning attention toward the principles of long-term sustainability. Operating in the pristine environment of space came with a profound responsibility, a principle deeply embedded in the factory's very DNA from its earliest design phases. This wasn't just about efficiency or cost saving. It was a fundamental commitment to stewardship, recognizing that the void beyond our atmosphere is not a dumping ground but a fragile commons that must be protected. The core philosophy was radical self-sufficiency, creating what engineers call a closed-loop system. Imagine a miniature world where almost nothing is wasted, where every output from one process becomes a valuable input for another. The most critical loops were for the basic elements of life itself. The air revitalization system was a masterpiece of chemical engineering, constantly scrubbing carbon dioxide from the atmosphere. But instead of just storing it, the system used a process called electrolysis to split the CO2 molecules, reclaiming precious oxygen for the crew to breathe, and even producing a small stream of carbon that could be used in manufacturing. Similarly, every drop of water was treated as a vital resource. Moisture from the air, sweat from the crew, and even wastewater were all captured and funneled into a multi-stage purification system that used a combination of filters, distillation, and catalytic reactors to render it perfectly clean and safe for drinking, cooking, and laboratory use. This wasn't just recycling, it was near-perfect regeneration, achieving an incredible 98% recovery rate and drastically reducing the need for constant, expensive resupply missions from Earth. This philosophy of circularity extended far beyond air and water into the very heart of the manufacturing processes. The factory was designed to be a voracious consumer of its own waste. Metal shavings from machining perfect alloy components weren't discarded. They were collected by magnetic sweepers, melted down in the microgravity furnaces, and reforged into new raw material stock. Even the byproducts of biological experiments found new purpose. Nutrient-rich waste from the tissue culture labs was carefully treated and then used to support a small onboard garden of plants, which in turn helped freshen the air and provided a psychological boost for the crew with a touch of living green. This relentless focus on reusing every possible material transformed the very concept of waste, viewing it not as an end product but as a resource temporarily out of place. It was a powerful demonstration of how industrial processes could be completely reimagined to work in harmony with their environment, rather than simply extracting from it. Powering this intensive industrial operation demanded an energy strategy that was both abundant and impeccably clean. The primary workhorse was, of course, the sun. The factory's vast solar arrays, with their acres of dark blue photovoltaic cells, harvested the uninterrupted, intense sunlight of space, generating many times the power a similar array could on Earth's surface, which is filtered through our atmosphere. But orbital night, that regular 45-minute period of eclipse, presented a challenge for continuous manufacturing. While massive banks of lithium-ion batteries smoothed over these brief interruptions, the true ambition lay in finding a constant, baseload power source independent of the sun's cycle. This led to the deployment of experimental compact fission reactors, small and incredibly safe nuclear units that provided a steady, unwavering stream of energy around the clock. Even more futuristic was the research into beamed power. In this concept, dedicated solar power satellites in a higher, sunnier orbit would collect immense amounts of solar energy and then transmit it wirelessly to the factory via highly focused microwaves or lasers, which would then be converted back into electricity. This would create a resilient, multi-source energy grid in space, a network where power could be generated in the ideal location and delivered exactly where it was needed, a concept that could one day revolutionize how we manage energy across the entire planet. Perhaps the most critical aspect of the factory's sustainability mandate was its unwavering commitment to not becoming part of the growing problem of orbital debris. Every component, from the largest module to the smallest tool, was designed with its entire life cycle in mind. Strict protocols governed every operation to prevent the accidental release of any object, no matter how small. But the most forward-thinking policy involved end-of-life planning. Any component that reached the end of its usable life wasn't simply jettisoned. Smaller parts and truly defunct equipment were carefully packaged into specialized containers. When enough had accumulated, these containers were loaded into a small, automated deorbiting vehicle. This vehicle would then fire its engines to slow down just enough to drop into a lower orbit, ensuring it would re-enter Earth's atmosphere over a remote area of the ocean, burning up completely and leaving no trace behind. For larger components that were still structurally sound, the preferred option was repurposing. A retired manufacturing module, for instance, might be stripped of its internal machinery and converted into additional storage space or even a dedicated greenhouse, giving it a second life and continuing to contribute to the facility's mission. This meticulous approach to debris mitigation set a new gold standard for responsible behavior in space, proving that industrial growth and a clean orbital environment were not mutually exclusive goals. The incredible success of these sustainability measures did more than just ensure the factory's own viability. It sent a powerful message back to Earth. The technologies perfected in orbit, the near-total water recycling, The hyper-efficient closed-loop manufacturing, the advanced solar power generation and wireless transmission became a blueprint for a new kind of industry on our home planet. Engineers and environmentalists studied the factory's systems as a living laboratory for the ultimate circular economy, adapting its principles to reduce waste and energy consumption in terrestrial factories, office buildings, and even entire cities. The Orbital factory became a powerful symbol, a tangible proof point that humanity's next industrial revolution didn't have to come at the expense of our environment. It demonstrated that the same ingenuity required to thrive in the harshness of space could be harnessed to live more lightly and wisely on Earth, turning the dream of sustainable industry from a distant aspiration into a working, breathing reality just overhead, shining as a beacon of what is possible when we choose to design with responsibility woven into every single decision. The stunning success of the first Orbital factory did not mark an endpoint, but rather a powerful proof of concept that ignited an era of unprecedented expansion. With the economic and scientific value of space-based manufacturing now irrefutably demonstrated, the vision rapidly evolved from operating a single, multi-purpose facility to constructing an entire networked constellation of specialized industrial parks in the sky. Planners armed with terabytes of operational data and hard-won lessons immediately began drafting blueprints for a second generation of facilities. These new designs were not mere copies. They were radical evolutions, each one purpose-built to dominate a specific industrial niche. Imagine a dedicated pharmaceutical factory orbiting in pristine silence, its entire environment calibrated for the zero-gravity synthesis of ultra-pure, complex protein-based drugs and vaccines that are impossibly delicate to produce on Earth. Envision another facility, a forge among the stars, solely focused on metallurgy, using the perfect mixing conditions of microgravity to concoct revolutionary new alloys and super-strong composite materials for next-generation aerospace and construction. This shift towards specialization promised to unlock staggering new levels of efficiency and product quality, transforming low Earth orbit from a novel laboratory into the galaxy's most advanced industrial zone. Every line on these new blueprints was informed by the sometimes painful, always invaluable experience of building and operating the pioneering first facility. The initial factory's modular design was praised, but the expansion blueprints took the concept even further. They envisioned larger, more robust central spines or backbones that could support not just more modules but heavier and more power-intensive industrial equipment. The lessons of robotic assembly led to designs that were even more robot-friendly, with standardized docking ports and internal rail systems that allowed maintenance and cargo bots to move through the structure with effortless speed. Crew habitats were redesigned for greater comfort and longer durations, incorporating more natural light, larger communal spaces, and enhanced radiation shielding based on the real dosage data collected from the first technicians. The goal was no longer just to make things work in space, but to make them work better, safer, and more efficiently than anyone had previously dared to imagine. These new facilities would be capable of hosting larger, more diverse crews of specialists and running a far wider array of simultaneous production lines, turning each new factory into a buzzing hive of multi-industry innovation. This ambitious expansion was never intended to be a solo endeavor. The model of collaboration that funded the first facility was now scaled up into a global partnership ecosystem. The same international space agencies that provided early grants were now signing on as anchor tenants and co-developers, bringing their deep expertise in long-duration spaceflight and orbital operations to the table. Private entities from aerospace giants to nimble biotech startups flocked to secure their place in this new industrial landscape, forming consortiums to fund the construction of specialized factories that would serve their collective needs. This was not a race with a single winner. It was the birth of a new economic sphere built on a foundation of shared infrastructure and mutual benefit. A company in Switzerland might fund the robotics for a new facility, while a university in Japan provides the research for its pharmaceutical production line, and a venture capital firm in Silicon Valley manages the overall operation. This collaborative spirit accelerated the pace of development exponentially, fostering a thriving ecosystem where competition drove innovation, but cooperation built the very platforms upon which that innovation could occur. The canvas for this expansion also grew vastly larger. While the first factory operated in a relatively accessible low Earth orbit, planners began looking further afield for even more advantageous real estate. Proposals were drafted for facilities in higher, more stable orbits that would offer longer periods of uninterrupted sunlight for solar power and clearer lines of sight for communications with Earth. The most visionary plans looked to the Lagrange points, those special gravitational sweet spots in space where the pull of the Earth and the Sun cancel each other out. A factory positioned at one of these points, like the famous L1 or L2 points, would require minimal energy to maintain its position, offering incredible operational stability. A facility at a Lagrange point could become a deep space gateway, a strategic hub for manufacturing fuel and components for missions heading to the Moon, Mars, or beyond. This wasn't just about finding more room in orbit. It was about strategically planting the flags of industry at the most valuable locations in the inner solar system, transforming the space between worlds into a highway dotted with rest stops, workshops, and power stations. This grand vision of a network of orbital industrial parks signaled a fundamental shift in humanity's relationship with space. It was no longer merely a destination for exploration or a venue for scientific discovery. It was becoming a central hub of economic activity, an integral part of our global industrial supply chain. The raw materials might come from Earth or one day from the Moon or asteroids, but the immense value would be added in the factories overhead, where the unique properties of space could transform them into products that improved life for everyone on the planet below. This expansive growth, however, hinged entirely on solving one of the oldest challenges of the space age, the daunting cost and complexity of transportation. Building one factory was a monumental achievement, but building a network would require a revolution in how we move people and cargo to and from orbit, making the next leap in logistics not just desirable, but absolutely essential for the dream to become a lasting reality. But a factory, no matter how advanced, is useless if it's isolated. The entire economic model of orbital manufacturing hinged on solving the final, most terrestrial of problems, the supply chain. The dream of a bustling industrial park in space would have remained just a dream without a revolutionary transportation network to reliably bridge the gap between our world and the void. This wasn't about the occasional, heroic Apollo-style mission. It was about creating a freight railroad to the stars, a system so routine and affordable that shipping a ton of material to orbit would become as predictable as shipping a container across an ocean. The driving force behind this revolution was the relentless pursuit of reusability. The astronomical cost of spaceflight had always been rooted in a simple, brutal fact. We were throwing away the entire airplane after a single transatlantic flight. That era ended with the sight of rockets landing themselves upright on landing pads or gently on drone ships at sea, their engines firing in a final, controlled burst to cancel their own destructive momentum. This wasn't just a neat trick, it was the single most important economic breakthrough in the history of space exploration. turning launch vehicles from disposable fireworks into reusable assets that could fly again and again, with only refurbishment and refueling required between missions. This new era of transportation was defined by a diverse fleet of vehicles, each designed for a specific role in the orbital ecosystem. For moving massive quantities of raw materials, the bulk metals, chemical precursors, and industrial feedstocks needed to keep the factory running. The workhorse became colossal spacecraft like SpaceX's Starship. Imagine a gleaming, stainless steel skyscraper lying on its side, capable of hauling over 100 metric tons of cargo into orbit in a single flight, and then returning to Earth to be reloaded within hours. For the more delicate task of transporting human technicians, a different class of vehicle emerged. Sierra Space's Dream Chaser, which looks like a miniature space shuttle, offered a much smoother, lower-G ride into orbit, landing gently on a runway like an airplane, which was far kinder on both its human passengers and any sensitive scientific samples they might be bringing back home. And for smaller, urgent deliveries, a specialized tool, a batch of experimental biological samples, or a critical replacement part, smaller, agile rockets from companies like Rocket Lab provided on demand, express delivery service to orbit, ensuring that the factory never had to halt production for want of a specific item. The true magic, however, lay in the seamless, automated handoff between these vehicles and the factory itself. This was where the concept of the automated cargo drone truly came into its own. These weren't piloted craft, they were intelligent, flying cargo containers. After being loaded and launched from Earth, they would navigate autonomously to the factory's orbital position, using onboard sensors and celestial navigation to approach with millimeter precision. The factory's own robotic arms, guided by advanced computer vision, would then reach out to gently capture the drone, guiding it to a standardized docking port. The process would then reverse for the return trip. Finished products, boxes of flawless crystals, vials of purified pharmaceuticals, or carefully packaged tissue samples would be loaded into empty drones. These would then undock, fire their own small thrusters to drop out of orbit, and re-enter the atmosphere protected by heat shields before deploying parachutes and landing at a predetermined recovery zone, often out in a remote desert. This created a continuous, automated conveyor belt running between Earth and space, one that required minimal human intervention and could operate around the clock. Managing this constant flow of traffic, both to and from orbit, required a logistics software platform of almost unimaginable complexity. This system had to be the central nervous system for the entire operation, a digital air traffic controller for near-Earth space. It didn't just track the location of every vehicle and every piece of cargo. It had to be a predictive, optimizing engine. The software would calculate the most fuel-efficient launch windows, not just based on the factory's orbit, but also on the orbits of every other satellite and piece of debris to avoid collisions. It managed the factory's inventory in real time, knowing exactly how much raw material was left for semiconductor production, or when the bioprinting lab would need its next batch of bioink. It could predict future needs based on the production schedule, automatically placing orders with suppliers on Earth and booking space on upcoming cargo flights weeks or even months in advance. This hyper-efficient coordination slashed wait times and eliminated costly delays, creating a just-in-time manufacturing flow that would be the envy of any terrestrial factory. A technician on the station could request a specific tool, and the system could not only locate one in a warehouse on Earth, but also book it onto a flight launching within days, with a precise estimated time of delivery to their hand. The ultimate result of this transportation revolution was a profound psychological and economic shift. the Orbital factory was no longer some distant, inaccessible outpost, a place only for government astronauts and billionaires. It became, in the most practical sense, just another node in the global supply chain. It was an off-world extension of Earth's economy, as accessible as a factory in another country, just with a much more interesting commute. This reliability was the final piece of the puzzle that unlocked the factory's true potential. Just-in-time manufacturing meant they didn't need to stockpile years' worth of expensive materials in orbit. They could order what they needed when they needed it, with the confidence it would arrive on schedule. This, in turn, enabled rapid iteration. An engineer on Earth could design a new alloy mixture, have the raw components shipped up on the next cargo run, oversee the production of a test batch from the ground via telepresence, receive the finished sample back within a week, and then immediately begin designing an improved version based on the results. This tight, rapid feedback loop between Earth-based design and space-based production accelerated the pace of innovation to speeds that were previously unimaginable, turning the Orbital factory from a mere production facility into a powerful engine for discovery. The products arriving back on Earth from the Orbital factory weren't just novelties, they were seismic shocks that began to reshape entire global industries from the ground up. The first and most immediate impact was felt in the world of technology, where the flawless semiconductors created in microgravity became the most sought-after components on the planet. Computer chip manufacturers, perpetually battling the physical limits of silicon, suddenly had access to a material that was fundamentally superior. These space-made wafers, with their perfectly ordered atomic lattices, allowed for the creation of processors that ran significantly cooler and could be packed with more transistors, effectively smashing through the performance ceiling that had begun to slow down Moore's law. The implications were staggering. Data centers that powered the global internet could achieve the same computational output with a fraction of the energy consumption, drastically reducing their massive carbon footprint. Artificial intelligence research, which was bottlenecked by processing power and heat generation, experienced a sudden leap forward, enabling more complex neural networks and bringing futuristic AI applications closer to reality almost overnight. Companies that secured early access to these space-made chips gained an almost insurmountable advantage, creating a new high-stakes tier in the global tech industry and sending a clear message: the future of computing was being forged in orbit. The revolution extended far beyond our gadgets and into our very bodies through the pharmaceutical industry. The ultra-pure protein-based drugs and vaccines synthesized in the weightless environment of the factory offered a level of efficacy and purity that was impossible to replicate in terrestrial labs. Without the distorting effects of gravity, complex molecules could form larger, more perfect crystalline structures, making them more stable, more bioavailable, and significantly more potent. This led to breakthrough treatments for a range of diseases, from certain cancers to neurological disorders, where medications could be administered in smaller doses with far fewer side effects and dramatically improved outcomes. One of the most celebrated early successes was a new form of insulin for diabetics, which offered a much smoother and more predictable control of blood sugar levels. The ability to consistently produce these perfect pharmaceuticals at scale in orbit didn't just mean better medicine. It also promised to lower long-term health care costs by reducing treatment times and hospitalizations, creating a powerful economic incentive alongside the profound human benefit. Perhaps the most visible impact for the average person was in transportation, driven by the advanced alloys and composite materials that were born in the orbital foundries. Aerospace companies were the first and most eager customers, integrating these new materials into the airframes and engines of the next generation of aircraft. The result was planes that were substantially lighter yet stronger, leading to double-digit percentage increases in fuel efficiency on every flight. This translated into lower ticket prices for passengers, reduced carbon emissions on a global scale, and extended range for routes that were previously not economically viable. The automotive industry quickly followed suit, using space-forged composites to make electric vehicles lighter, which in turn extended their battery range and reduced wear on tires and brakes. The ripple effects touched everything from the design of high-speed trains to the construction of more efficient wind turbine blades, demonstrating how our innovation in space-based materials science could accelerate the green transition back on Earth. This influx of revolutionary products created a powerful and self-sustaining economic engine. The Made in Space label commanded a significant premium, and the profits from these high-value goods were funneled directly back into funding further space ventures, creating a virtuous cycle of investment and innovation. More importantly, it spawned entirely new, high-skilled job sectors on Earth. While the factory itself was highly automated, it required a massive ground-based support ecosystem. Teams of remote operators, data analysts, logistics coordinators, maintenance programmers, and specialized engineers who monitored the systems and interpreted the vast streams of data. Universities launched new degree programs in space-based manufacturing and orbital logistics, training the next generation of workers for an industry that simply hadn't existed a decade prior. This wasn't about jobs leaving Earth. It was about the creation of a new, high-tech industrial spine that reached into orbit and back, employing thousands and fostering a new wave of economic growth. The influence of the orbital factory also triggered a wave of innovation in terrestrial manufacturing methods. The extreme constraints of building in space, the need for perfect efficiency, closed-loop systems, and lightweight materials forced engineers to develop solutions that were brilliantly elegant and minimalist. These space-derived techniques began to trickle down to factories on Earth. The advanced predictive maintenance algorithms used to monitor the factory's health were adapted to predict failures in power plants and assembly lines, preventing costly downtime. The ultra-efficient water recycling systems became a model for water-scarce regions looking to conserve resources. Even the modular, plug-and-play design philosophy of the factory's architecture influenced the construction of new, more adaptable industrial facilities on the ground. This cross-pollination of ideas proved that the greatest value of the orbital factory might not just be the products it sent down, but the radical new ways of thinking it inspired, pushing industries everywhere to operate smarter, cleaner, and more efficiently. Yet this breathtaking ascent into a new industrial age brought with it a host of profound and complex questions that reached far beyond engineering and into the very heart of our values as a global society. The simple, thrilling fact that we could manufacture in space immediately forced a much more difficult conversation. How should we do it? The void above our planet, once considered an empty expanse, was now a workplace, a resource, and a fragile environment requiring protection. This new reality demanded the creation of a first-of-its-kind rulebook, a set of ethical principles and international regulations crafted not from abstract theory, but from the urgent, practical need to ensure this powerful new capability would benefit all of humanity, not just a privileged few. One of the most heated and vital debates centered on the fundamental principle of equitable access. The fear was that the staggering costs of reaching orbit would naturally create a new form of high-tech colonialism, where only the wealthiest nations and most powerful corporations could own and operate these lucrative off-world facilities, reaping the profits while the majority of the world was left as mere consumers. To prevent this, a landmark international treaty, often called the Orbital Commons Accord, was drafted and ratified by over 100 nations. This agreement established that low Earth orbit itself was a shared resource, akin to the high seas or Antarctica. It did not prohibit private ownership of factories, but it mandated that a percentage of all manufacturing capacity, perhaps 5 to 10%, be reserved for use by an international consortium of developing nations and non-profit research institutions. This ensured that a university in Kenya or a public health initiative in Bolivia could access orbital manufacturing for critical research or humanitarian projects, guaranteeing that the benefits of this new frontier would ripple across the entire globe, not just accumulate in a few corporate headquarters. This spirit of stewardship extended to the environment, both in space and on Earth. The old, careless mentality of treating space as an infinite dumping ground was categorically rejected. New and stringent regulations were imposed, requiring that every component of every orbital facility be designed with its entire life cycle in mind. Strict debris mitigation protocols became legally binding. Defunct equipment couldn't simply be jettisoned. It had to be either carefully deorbited to burn up in the atmosphere or moved to a designated graveyard orbit. The factories themselves were subject to environmental impact assessments, evaluating their effect on the orbital lanes and even their potential to contribute to light pollution for astronomers on the ground. Furthermore, the products themselves faced scrutiny. To prevent simply shifting Earth's pollution to space, regulations required that the energy-intensive process of launching materials be offset by the demonstrable environmental benefits of the products made in orbit, such as the massive energy savings from more efficient semiconductors or the reduced waste from purer pharmaceuticals. Perhaps the most human-centered of these new frameworks addressed the rights and protections of the orbital workforce. These were not astronauts on short-term scientific missions. They were technicians, engineers, and factory operators living and working in space for extended rotations, essentially becoming the first off-world industrial laborers. A whole new branch of labor law had to be imagined from scratch. What constitutes a fair workday in a place where the sun rises and sets 16 times a day? How do you define overtime pay when your workplace is traveling at 17,000 miles an hour? International agreements established a standard based on coordinated universal time, ensuring clear rules for rest periods and work hours. Health and safety protocols went far beyond anything on Earth, with mandatory, frequent medical monitoring and an absolute right to evacuation for any crew member who felt their health was at risk. Crucially, these space-based workers were granted the full legal right to organize and collectively bargain, ensuring their voices would be heard in the development of the protocols that governed their extraordinary working lives. For the most sensitive technologies, like the bioprinting of human tissues, the response was the formation of independent international ethics committees composed of scientists, doctors, philosophers, and religious leaders. Their thankless task was to navigate the murky waters between incredible opportunity and profound ethical risk. They established clear boundaries, such as an absolute and universal ban on any attempt to print a developed human organ without a specific, life-saving medical need and recipient. They created rigorous consent procedures for any human cells used in research, ensuring they were ethically sourced. These committees didn't exist to stifle innovation, but to build a central guardrail of trust around it, ensuring that society would embrace these amazing advancements with confidence rather than fear. Finally, to bring order and safety to the marketplace, new global regulatory bodies were established. These agencies, developed in partnership with existing entities like the World Health Organization and the International Air Transport Association, created the first certification standards for made-in-space products. A vial of medicine produced in orbit had to undergo even more rigorous testing and purity verification than its terrestrial counterpart to earn its certification seal. A structural component made from a new space-forged alloy had to meet universally recognized safety standards before it could be used in an airplane or a medical implant. This certification process was vital. It transformed these novel products from exotic curiosities into trusted, reliable goods that could be integrated into the global supply chain, giving consumers, engineers, and doctors the confidence to use them. The collaborative spirit that forged these multifaceted frameworks was in its own way as stunning an achievement as building the factory itself. It demonstrated that humanity could not only reach new frontiers technologically, but could also learn to govern them with wisdom, foresight, and a shared commitment to a better future for everyone on the planet below. The Orbital factory's journey wasn't confined to mission control centers and scientific journals. It blossomed into a truly global phenomenon, a shared human achievement that played out on the screens and in the classrooms of millions around the world. This wasn't just about building a factory, it was about building a connection. For the first time in history, the public wasn't merely watching a historic event. They were living inside it, thanks to an unprecedented commitment to transparency and access. A constellation of high-definition cameras mounted both inside and outside the facility provided a continuous, unscripted live feed of daily operations. People could tune in during their morning coffee to watch a robotic arm perform a delicate repair against the breathtaking backdrop of a rising sun over the Pacific Ocean, or witness the quiet concentration of a technician during a bioprinting experiment in the evening. This raw, intimate access transformed abstract concepts into tangible reality. A student in Mumbai could see the same flawless silicon crystal being extracted from its growth chamber as an engineer in Houston, dissolving the distance between the dream and the audience, making everyone a virtual participant in the grand endeavor. This direct access was powerfully augmented by immersive virtual tours that took public engagement to a whole new dimension. Partnering with leading virtual reality platforms, the project created incredibly detailed digital twins of the entire facility. Anyone with a VR headset or even just a smartphone could embark on a self-guided tour, floating through the modules with complete freedom. They could zoom in on the intricate details of a manufacturing furnace, read the digital displays on control panels, or step inside the cupola to experience the awe-inspiring panoramic view of Earth that the crew enjoyed every day. These weren't passive experiences, they were interactive adventures. Users could trigger informational pop-ups explaining the science behind each station, or even try their hand at simple, gamified versions of assembly tasks, like docking a virtual module or aligning a solar panel. This hands-on virtual access did more than just educate. It fostered a deep, personal sense of place and ownership, making the Orbital factory feel less like a distant government project and more like a place you had visited and understood. Recognizing that the future of this new frontier depended on inspiring the next generation, a massive global educational initiative was launched in parallel. The project's outreach team worked directly with educators to develop comprehensive curricular packages for all grade levels, seamlessly weaving the science of the Orbital factory into subjects like physics, chemistry, biology, and even economics. Elementary school students received activity kits to design their own microgravity experiments with simple materials, while high schoolers could access real, anonymized data streams from the factory to use in their science projects, analyzing crystal growth rates or energy consumption patterns. The most popular program was undoubtedly the annual Call to Orbit video contest, where student teams would propose a new experiment to be conducted on the factory. The winning team wouldn't just get a prize, they would earn a dedicated time slot on the facility's schedule, work with an engineer mentor via video link to finalize their proposal, and then watch live as astronauts or robots executed their experiment hundreds of miles above their classroom. This program produced some of the project's most heartwarming and viral moments as kids saw their own ideas, from testing spider web formation in zero-G to growing perfect crystals of common salt become part of space history, proving that great ideas could come from anywhere. The human stories behind the steel and glass were given a powerful spotlight through a series of deeply personal documentaries and a shrewd, heartfelt social media strategy. Instead of focusing solely on the technology, these narratives followed the individuals. The lead designer who had sketched the first concepts on a napkin decades earlier, the young welder from Ohio who had crafted a critical component with her own hands, the microbiologist who had spent years perfecting the bioprinting process, and the astronauts who called the factory their temporary home. Social media channels offered a more informal, daily look at life aboard the station, from a technician's hilarious attempt to master a simple task in weightlessness to their quiet, profound reflections on the view of home. These stories did something crucial. They put a human face on an incredibly complex technological achievement. They showed the years of dedication, the moments of frustration, the camaraderie, and the sheer joy that powered the mission. People weren't just supporting a factory, they were cheering for Sarah the engineer and Louis the astronaut, making the entire project feel relatable and deeply human. This sense of collective ownership was made tangible through initiatives that invited the public to literally leave their mark on the project. A global campaign was held to name the major modules, with millions of people submitting and voting on suggestions. The winners weren't chosen by a committee of executives, but by popular vote, leading to names that reflected a global perspective like the Unity Hub, the Curiosity Laboratory, and the Endeavour Manufacturing Bay. Even more impactful was the opportunity for the public to influence the factory's research agenda. Several times a year, a list of potential future experiments would be published online, and people could vote on which one should be prioritized. Should the factory focus next on a new alloy for safer cars or a pharmaceutical study for a rare disease? By giving the public a direct voice in these decisions, the project fostered an incredible sense of shared stewardship. It was no longer their factory, it was our factory, a collective project for all of humanity. This widespread, enthusiastic engagement did more than just build a fan base. It built a durable foundation of political and public support that guaranteed funding would continue and that the dream wouldn't end with a single facility. It transformed the Orbital factory from a marvel of engineering into a potent global symbol of unity, curiosity, and our limitless potential when we choose to work together, setting the stage for a celebration that would feel less like a corporate milestone and more like a planetary birthday party. After years of relentless effort, a hush fell over mission controls around the world. A collective breath held as the final system status check scrolled across countless screens. Then the moment arrived. A single command issued from a console in Houston formally changed the Orbital factory's status from commissioning to fully operational. And with that, the world exhaled in a wave of pure, unfiltered celebration. This was not a quiet turning of a key. It was a planetary party, a historic day where the abstract dream of decades finally crystallized into a functioning, productive reality. Live broadcasts became windows to a shared human triumph, cutting between the gleaming, weightless interior of the factory itself, where crew members high-fived in slow motion, and gatherings of the key figures who made it all possible. In a packed auditorium at the European Space Agency, an elderly engineer who had worked on the earliest conceptual designs wept unashamedly as the news broke, his decades of belief finally vindicated. At the headquarters of the private startups that had bet their entire existence on this moment, champagne corks flew, not in slick corporate boardrooms, but in bustling, open-plan offices where every employee had a personal stake in the outcome. The ceremonies were a testament to the project's truly global nature. There was no single central venue. Instead, the celebrations were a networked event, a mosaic of humanity. In Tokyo, a ceremony honored the material scientists who developed the radiation-resistant alloys. In Cape Canaveral, launch teams who had flawlessly sent every module on its way were cheered by their families. And in space, the factory's crew hosted their own solemn and awe-inspiring event, floating before a camera with our entire planet serving as their backdrop. They spoke not of national pride but of shared purpose, their voices occasionally cracking with the emotion of representing all of humanity in that moment. The most powerful moments came when the video feeds would split screen, showing a young intern at Mission Control in Germany watching an astronaut she had trained, now smiling back at her from orbit. This visible connection made the vast distances feel intimate, collapsing the space between the dreamers on the ground and the builders in the sky. Then came the unveiling, a moment designed to translate this monumental achievement into something tangible. In a carefully staged presentation, the first batch of commercially sold space-made products were revealed. It wasn't a flashy corporate showcase. It was presented with the reverence of a museum exhibit. Under glass cases on Earth sat the results of that very first manufacturing test. Several pristine silicon ingots, looking like bars of metallic ice, each accompanied by a data readout showing their unprecedented purity. Next to them were vials containing the first commercially available pharmaceuticals synthesized in microgravity, and a small, impossibly light disk of a new superalloy. These weren't prototypes or samples. They were the first production run, already sold to partners and earmarked for research and development that would change industries. Seeing these physical objects, knowing they were forged in the void above, made the factory's purpose instantly and powerfully clear to everyone watching. This was the dawn of a new economic era, and these were its first artifacts. The speeches that followed across the globe struck a consistent, hopeful chord. A former astronaut, now leading a national space agency, spoke of the factory as a symbol that our greatest conflicts on Earth could be set aside for a common goal that lifted everyone. A CEO who had been an early investor recounted the skepticism they faced and praised the thousands who proved the skeptics wrong. But the most resonant words came from the project's original visionaries, the ones who had been called fools for dreaming of factories in space. They didn't speak of profit margins or technological supremacy. They spoke of destiny and responsibility. They framed the factory not as an end, but as a beginning, the first proof that humanity could learn to live off the planet not just as visitors, but as creators. They emphasized that this was a project of peace and progress, built by a generation that chose to look up and build together, rather than look down and argue. As the ceremonies on Earth began to wind down, the broadcast feed cut to a final, breathtaking shot from a camera mounted on the outside of the factory. The sun dipped behind the curvature of the Earth, plunging the structure into orbital night. For a moment, it was a silent, dark silhouette against the infinite starfield. Then, light by light, the factory's external illumination system powered on. Its thousands of windows and running lights began to glimmer, outlining the entire magnificent structure against the profound blackness of space. It was no longer just a collection of modules. It was a single, coherent beacon, a delicate necklace of light slowly drifting across the heavens. Anyone with a clear night sky could step outside, look up, and with a simple pair of binoculars, see it, a tiny, moving star that was not a natural phenomenon, but a sign of what we can accomplish. This day was so much more than a factory going online. It was a signal fire lit for the future, a declaration that humanity had taken its first conscious, permanent step into the cosmic ocean, not merely to explore but to stay and to build. The celebrations, while honoring the past, were inherently focused on the horizon, using this milestone as a solid foundation from which to launch the next, even more ambitious phase of the journey. Yet this magnificent facility, this city of industry silently circling our world, was never meant to be a final destination. It was designed from its very first bolt to be a prototype, a training ground, and a powerful springboard for a vision so grand it once existed only in the most optimistic pages of science fiction. The long-term goal, the true north that has guided every decision, is nothing less than the transformation of humanity into a truly multi-planetary species. This orbital factory is the crucial first chapter in that story, the proof that we can not only live in space, but that we can work and create there, building the tools we need to journey farther than we ever have before. The next logical step in this expansion is already taking shape in simulation labs and design studios across the globe. Lunar factories. The moon presents a tantalizing opportunity, a nearby world with 1/6 of Earth's gravity and a surface rich in raw materials. Imagine facilities built in the permanently shadowed craters at the lunar poles, where water ice can be harvested and split into liquid water for life support and hydrogen and oxygen for rocket fuel. These wouldn't be just outposts, they would be gas stations and supply depots for the solar system, drastically reducing the cost and complexity of deep space missions by providing fuel and materials that don't have to be launched from the bottom of Earth's deep gravity well. The lessons learned from building and automating the orbital factory, the robotic assembly, the closed-loop life support, the remote management are the exact same skills needed to establish these first industrial footholds on another world. Beyond the moon lies the ultimate prize for heavy industry, the asteroid belt. This sprawling ring of cosmic rubble is not just a hazard to be avoided, it is an almost unimaginable treasure trove of resources. These asteroids are the leftover building blocks of our solar system, containing vast quantities of precious metals like platinum, gold, and cobalt, as well as more fundamental resources like iron, nickel, and water. The vision is to develop autonomous robotic spacecraft that can rendezvous with these asteroids, mine them for their raw materials, and then either process them on site or transport them to strategically located orbital refineries. This concept, known as in situ resource utilization, would completely rewrite the economics of spaceflight. Instead of expending enormous energy to launch every single gram of material from Earth, we could essentially mine the sky, constructing massive spacecraft and space stations from materials that are already in orbit, making projects that are currently fantastically expensive suddenly achievable. The ultimate expression of this interplanetary industrial network would be a permanent, self-sustaining colony on Mars. This is not about planting a flag and leaving footprints. It's about building a second home for humanity. The Martian colony would be the culmination of everything learned from every prior step. It would need its own factories to produce everything from building materials, using the red planet's own soil, to food, air, and water. The manufacturing processes perfected in the microgravity of the orbital factory would be adapted to Mars's lower gravity to create structures and technologies that can withstand the harsh Martian environment. This colony would be the first test of whether an entire community can truly live independently off-world, a breathtaking experiment in biology, sociology, and engineering that would secure humanity's future against any single-planet catastrophe. This vast, interconnected industrial network, spanning from low Earth orbit to the asteroid belt, promises to solve some of Earth's most persistent challenges. By moving the most energy-intensive and polluting industrial processes off-planet, we could begin to heal Earth's environment, allowing our home world to focus on sustainability and restoration. The abundant clean energy and limitless resources of space could end scarcity on Earth, providing the materials needed to build a global infrastructure of clean water, reliable energy, and advanced technology for everyone. The opportunities for exploration would be equally profound. With a steady supply of fuel and parts available throughout the solar system, missions to the outer planets and their fascinating moons would become routine, opening up new frontiers for scientific discovery that we can currently only dream of. This future, which for so long felt like the stuff of dreams, now feels tangibly within our grasp. It is a future built not on solitary genius, but on the power of perseverance and global collaboration. The Orbital Factory stands as a shining testament to what we can achieve when we choose to look up and work together, a beacon guiding us toward our destiny among the stars. It reminds us that the greatest journeys begin with a single, determined step, and that the next chapter of our story is waiting to be written, not on paper, but in the silent, endless expanse above us. From visionary blueprints to breakthrough operations, the story of Earth's first orbital factory is a testament to human ingenuity and determination. We've traversed a timeline filled with challenges overcome, technologies perfected, and milestones achieved. This factory not only revolutionized manufacturing but also redefined our relationship with space, turning it into a realm of economic and scientific opportunity. As we look to the future, let this achievement inspire us to dream bigger and collaborate broader. If you enjoyed this journey, like and subscribe for more deep dives into humanity's next frontiers. Share your thoughts in the comments. What should we manufacture in space next? Thank you for watching, and remember, the future is what we build.